Welcome to the world of artificial intelligence, where machines don't just follow instructions, they learn, adapt, and make decisions on their own. At the heart of this digital transformation lies one of the most fascinating developments in computer science: neural networks. Modeled after the human brain, neural networks allow computers to recognize patterns, process information, and even simulate human-like thinking. But what exactly are they? How do they work? And why are they such a foundational part of modern AI? Let's dive deep and decode the brain behind the machine. What is a neural network? Imagine how the human brain works. Billions of neurons pass electrical signals, helping us think, remember, and act. Now imagine creating a digital system that mimics this behavior. That's a neural network. It's a type of machine learning model designed to process data, identify patterns, and make decisions based on experience, just like a brain. These networks are composed of layers of tiny computing units called nodes, or artificial neurons, which are interconnected. Each neuron receives data, performs a simple computation, and passes the result to the next layer. With enough data and training, neural networks can identify faces, translate languages, play chess, and even drive cars, all by learning from past experiences. The anatomy of a neural network. Let's take a closer look at how a neural network is structured. There are three main types of layers. Input layer. This is where data enters the network. It might be a set of numbers, pixels from an image, or words from a sentence. Hidden layers. These layers lie between the input and output. They perform complex calculations and learn features from the data. Some networks may have just one hidden layer, while deep learning models can have dozens. Output layer. This produces the final result, like a classification or prediction. Every connection between nodes has a weight, which determines the importance of a given input. There are also biases, which help adjust the output. Through training, these weights and biases change, enabling the network to make better predictions. How neural networks learn. But how does a neural network actually learn? It starts with training, the process of feeding data into the network and teaching it to recognize patterns. Initially, the network makes random predictions. It compares these to the actual answers using a loss function, a way to measure how far off it was. Then comes the magic: backpropagation. This technique sends error signals backward through the network, adjusting weights and biases using an algorithm called gradient descent. Over many iterations, the network learns to reduce its mistakes, becoming more accurate over time. Just like we improve at a task through practice and feedback, neural networks refine their knowledge through continuous training. Real-world applications. Neural networks are no longer confined to research labs. They're everywhere in our daily lives. Let's explore some real-world applications. Voice assistants. When you speak to Alexa, Siri, or Google Assistant, neural networks help transcribe and understand your voice using speech recognition. Recommendations. Platforms like YouTube, Netflix, and Spotify use neural networks to analyze your behavior and suggest content tailored to your preferences. Healthcare. Neural networks can analyze X-rays, MRIs, and genetic data to help doctors detect diseases earlier and more accurately. Finance. In banking, they monitor transactions to detect fraud, and in stock markets, they forecast trends based on historical data. Transportation. Self-driving cars rely on neural networks to interpret road conditions, identify pedestrians, and make split-second decisions. Creativity. AI can now generate realistic art, compose music, and even write poetry, all thanks to neural networks trained on massive creative datasets. These are just a few examples. The possibilities are growing every day. Deep learning and neural network variants. Let's go a layer deeper, quite literally, into deep learning. Deep learning refers to neural networks with multiple hidden layers. These deeper architectures allow for more complex and abstract representations of data. There are also different types of neural networks for different tasks. Convolutional neural networks, CNNs, are excellent at processing images and video. They scan visual data in layers, recognizing shapes, objects, and textures. Recurrent neural networks, RNNs, are used for sequential data like speech, language, or time series data. They remember previous inputs, making them great for things like language translation or speech recognition. Transformers, the latest breakthrough, are now powering large language models like ChatGPT and Google Bard, enabling deep contextual understanding of language. Each type has its strengths and is optimized for specific kinds of data and problems, strengths and limitations. As impressive as neural networks are, they're not perfect. Strengths. They excel at pattern recognition. They can learn from vast amounts of data. They generalize well to new situations, in many cases, but there are limitations. They require massive data sets and computing power to train effectively. They can suffer from overfitting, where they memorize training data but fail on new inputs. They're often black boxes, meaning we don't always understand how they arrive at a decision. And they're vulnerable to adversarial attacks, where small, imperceptible changes in data can lead to wildly inaccurate results. These challenges have sparked research into explainable AI, fairness, and robustness, all to make AI more trustworthy and reliable. The future of neural networks. So, what does the future hold for neural networks? We're moving toward explainable AI, where neural networks can justify and explain their decisions, a key step for safety, ethics, and trust. We're also seeing progress in neuromorphic computing, building chips that mimic the brain's energy efficiency and architecture. Future networks will be more efficient, interpretable, and embedded in everyday objects, from smartphones to wearable health devices. They could revolutionize education, agriculture, environmental monitoring, and even space exploration. And as quantum computing and AI merge, entirely new forms of intelligence may emerge, ones that go beyond what we can currently imagine. The frontier is wide open. Neural networks are the invisible engines powering modern AI, quietly analyzing, predicting, and learning across nearly every industry. They're not just lines of code. They're dynamic systems that adapt and evolve with every new byte of data. As we continue into this new era of intelligent machines, understanding how they work is more important than ever. Because in many ways, the future of intelligence might not just be human. Thank you for watching. Don't forget to like, share, and subscribe for more deep dives into the tech shaping our world.